Hi folks, and welcome to this video on percent concentration. Before we get started, I want to present a scenario to you. I have a bottle of pop, and one of these I've poured the pop into. The other one, and I'm not going to tell you which one, the other one I poured a little bit of pop in some water. In other words, one of these is diluted and one of these is not diluted. Can you tell which one? I think most of you will guess that this one on the left, this is the one that is diluted. And I think you can tell that by the color. Now, if you tasted them, you could probably confirm, yeah, this is the one that was not diluted, this one was diluted. So we have an intuitive sense, through taste and color and some other ways of determining whether something is more concentrated than something else. What we'd like to do in chemistry is we would like to look at some other ways of talking about concentration, just besides just an intuitive way. And the way we're going to do that is we'll start out with some percent formulas. Now, I've got 3 of them here, but I'm just going to concentrate on the first one to begin with. And this is a percent weight per volume. And notice the way we write this, a W/V percent, weight per volume. Now, remember, weight is always going to have the unit grams, and the volume is always going to have the unit milliliters. If you can remember that, these next 2 equations are very easy. And of course, because this is a percent, it's times 100. So it's going to be weight in grams of the solute, that's the substance being dissolved, divided by the volume in milliliters of the solution. Okay, and now these ones we can also do a volume per volume. That would be milliliters of solute divided by milliliters of solution. This is convenient if the solute is another liquid. And then we have weight per weight. This would be something where it's easier to say measure the weight of the solute in the solution rather than the milliliters. Okay, let's actually see how we would use these equations. Let's look at some problems. Okay, so let's start with the first problem. How many grams of potassium chloride are required to make a 7.25% weight per volume aqueous solution in a 250 milliliter volumetric flask? Okay, first thing, let's come up with that equation. We're talking about a weight per volume, percent weight per volume. So let's just start by writing that equation. That is weight per volume percent is going to equal grams of solute divided by milliliters of solution, and then times 100. So let's just substitute things directly into our equation. We know that we have our percent. It's going to be 7.25. Just taking that from there. Let's see. We have the volume. That's 250 milliliters of solution. And we've got our, okay, how many grams of potassium? So the grams, this is what we don't know. Okay, so I'm just going to put an X there for what we don't know. And then, of course, this is times 100. So let's just solve it as is. First, I want to get this X by itself. So I'm going to divide both sides by 100. So that's pretty easy. Just going to move the decimal point 2 places, 1, 2. Equals X over 250 point. And I think you can see at this point, we're going to multiply both sides by 250. So I have X equals 0.0725 times 250 point. And I can punch that out on the calculator. And I get, let's see, 0.0725 times 250, and I get 18.1 gram of potassium chloride would be in 250 milliliters to give me a 7.25% solution. Okay, let's try the next one. How many grams of iron 2 iodide are there in 436 grams of an aqueous solution that is 24.3 weight per weight percent iron 2 iodide? Okay, I'm going to do the same thing. I'm going to start by just my equation, by writing my equation. So let's start with that. Now, notice this is a weight per weight. Okay, let me just write that, weight per weight percent. Remember, the weight is always going to have the unit gram. So it's going to be grams of solute divided by grams of solution times 100. And let's just go ahead and substitute in what we have here. We've got 24.3 weight per weight percent. So that's going to be 24.3 equals, and we're looking for the grams again, right there. And we've got 436 grams of an aqueous solution. So notice that it's not milliliters. In this case, it is grams. And of course, that's all times 100. So we're going to solve it the same way we solved the last problem. We are going to divide both sides by 100. So this is going to become 0.243 equals x divided by 436. Then you can see I'm just going to multiply both sides by 436. So I get 0.243 times 436 equals x. And when I punch that out, I get 0.243 times 436 equals, and I get an answer of equals 106. It's going to round off to 106 grams of, in this case, it was iron 2 iodide, grams of FeI2. Okay. Next question. How many milliliters of water would be required to prepare the solution in problem 2? In other words, this problem right here. Well, let's think about it. This solution, in problem 2, we had a solution that weighed 436 grams. Let me write this down. The solution was 436 grams. And they're asking us here how many grams of water are required to prepare the solution. Well, the water is going to be the solvent. And remember that all solutions are made up of two parts, the solute and the solvent. So if I know the part that I know the total, this is the total, the solution, and I figured out in the previous problem how much of that was solute, then I can figure out by subtraction how much is going to be solvent. So the solution minus the solute, in this case it was 106 grams, is going to give me the grams of the solvent. And in this case, it's going to be, do a little bit of subtraction, we get 330 grams of water. Okay, now let's go back to that problem. We're not done. We figured out it's going to be 330 grams of solvent, of water, but they're asking for milliliters. So we need to convert that grams of water, that 330 grams of water, we need to convert that into milliliters of water. Now these are interesting units, grams and milliliters. Those are the units that we use in density. So the density of water is one that we know, we should know. 1.00 gram for every 1 milliliter. That's the density of water. You know what? I have this upside down. Can you see that I have it upside down? The grams won't divide out. And I won't get the units of my answer either. So let's fix this. It's going to be 1 milliliter for every 1.00 gram. Now I think we're ready. Grams of water will divide out. Milliliters is left, which is what I want for my answer. The math here is going to be really easy. Times 1 divided by 1. In the case of water, at least the math is real easy. So it's going to be 330 milliliters of water that I would need to make that solution. Okay, folks, that wraps up my examples of percent concentration. I hope that was useful.